I can't hear you.
You can't hear me. Wait.
Oh my goodness. Hi.
Now you can hear me.
Hello. Hello. I can hear you now.
Can you not hear me at all?
No, I can hear you now. Can you hear me now?
Oh, yeah, it's great.
Okay. Yeah, I have to adjust volumes and everything, and I have to adjust your
All
volume.
the things.
All the things, you know.
The sliders and the knobs and the dials.
You know how it goes.
Yeah, it's super annoying.
I know. So I was just talking about black holes with everybody. We were watching.
That's cool.
Yeah.
Black holes are nice. I'm a fan.
Yeah, can everybody hear Dr. Paul okay? You guys can't see him yet. Don't worry, I'm working on that too.
They say I'm too loud.
Okay, well, I'm turning him down.
Sorry.
No,
I can just be really quiet.
Wait, let's see. Okay, keep talking. You have to keep talking.
I'll just keep talking. Honestly, I like black holes. I'm a fan, not against them at all. Honestly, I think neutron stars are more interesting.
Why is that?
Because neutron stars have some crazy physics inside of them. So do black holes. But black holes are relatively simple.
Mm-hmm.
But neutron stars are complex on a variety of levels. And they have the pasta.
The pasta?
The nuclear pasta.
What?
So this is the best thing in the world.
Okay.
Inside of a neutron star, so there's a crust, like a crunchy outer shell of a neutron star. If you punch through that, at the extreme temperatures and pressures inside of a neutron star, the neutrons, it's not just like a soup. They squish down and form shapes. And at different layers, they form different kinds of shapes. And there's one big layer where they form, like there's tubes of neutrons that all intertwine together, and they call it the nuclear pasta.
I've never heard that. So
it's amazing.
That sounds amazing. Along with the term spaghettification.
Mm-hmm.
Have you ever? I mean, just
physicists are very hungry.
Yeah, I feel that's they are. Okay, I think we have everything. We got everything working now. I think. Let's see. So this is Dr. Paul, guys. And he's on every Tuesday. You know, granted, again, that nothing comes up. And he has his own link in here. You guys can see all of the links to all of his stuff.
I do stuff. There's a pasta stuff.
Yeah.
Complex intertwined tubes of science communication.
Mm-hmm. Mm-hmm. So we're kind of, I think, you know, right now the chats, we're kind of on this topic of black holes. We were just talking about all kinds of things. Where in the documentary we just watched, they said that new stars couldn't really form close to a supermassive black hole, but you and I, we had to talk about that on your space radio.
We did talk about that, didn't we?
Yeah, about that black hole swarm.
Yeah. So it's a good question. Like, what did the documentary mean by close?
Yeah, and that's kind of what I was wondering too. I wonder if they mean, you know, because that was like within 6 light years or something.
Okay. I'm
thinking that's where, I mean, I don't remember exactly the distances. If anybody wants to Google that real quick to see how close that black hole swarm was, it's from May. Just Google black hole swarm, and you'll probably get it.
What was the documentary?
It was called, what was it? Black Hole Apocalypse by Nova.
Black Hole Apocalypse.
It was very, very awkward to watch, but I think it did provide pretty good information.
Sounds awkward.
It was
just
very
the title.
Yeah.
So the deal with these supermassive black holes is that when material falls in, the material heats up on its way to being eaten. That sends out a huge blast of radiation, which heats the surrounding material and blows it away and kind of prevents stars from being formed. Stars need cold, dense, quiet pockets to collapse in on themselves to form stars. And if you heat up the gas and you blow it away, you can't form stars. So we're pretty sure, we're not 100% sure, we're pretty sure there's a link between supermassive black hole activity and star formation in the host galaxy itself.
Right. And I'm trying to, now I pulled it up. Oh, okay. So the X-ray spectra was about within 12 light years.
There you go.
Yeah. So, yeah, that's pretty impressive. And so that implies what? Because you asked me this on yours, and I'm going to ask you. What does that imply? What does that mean to have these stellar mass black holes close to our supermassive black hole, relatively?
Or like like all these big black holes, it means there is a ferocious amount of star formation happening in the galactic core. Or it means that a lot of material, like a lot of stars, are being formed outside the core and then being pulled in, and that the relationship between supermassive black holes and their environment is much more complicated than we had thought.
That is exactly. I mean, so it opens up more questions.
That's exactly what you said. Really, I just played it back in my head and said it out loud.
It took me like 10 minutes to get to that answer, though. Can a black hole ever die? And that actually goes in line with someone says right above that, Kinker says, do we know what happens to the mass of a black hole when it dies? And yes, they can die.
Yeah, we're pretty sure they died. This is Stephen Hawking's big deal, developed in the 70s, where due to complex and nearly impossible to explain interactions between a black hole event horizon and the fundamental quantum fields that make up everything, black holes leak. They glow just a little bit. They lose a little bit of mass incredibly slowly. We're talking like 1 photon a year. So for a typical stellar mass black hole, we're talking 10 to 100 years at least before it appreciably evaporates, and it just gets smaller and smaller and smaller and smaller. And the smaller it gets, the faster it evaporates, and then it just goes. I'm not sure on the sound. Yeah, but that's the idea.
Yeah, it's probably not going to have. I think I wrote down trying to explain it because I want to be able to explain Hawking radiation, but it's really difficult, like you said, to explain simple.
Hawking radiation is really tough to explain. And the typical explanation of, oh, there's pair production in the event horizon, one gets pulled in and one gets ejected, and then therefore the black hole loses mass.
It's like you have a particle and antiparticle, right? One has positive mass, the other one has negative mass.
Negative charge.
Negative charge. And so they actually, create each other, but then they break away from one another. And they split apart, right? And then they cancel each other out. They annihilate each other.
Yeah, so this kind of, I'm not a big fan of this idea, this picture of pair production happening in the vacuum anyway. I prefer a more fundamental field view of it. But in this pair production picture, in the pure vacuum, in between all the stuff, particles are constantly being created and destroyed all the time. And they come in pairs. You get a particle and its antiparticle can just pop magically out of the vacuum for no reason at all. And then they'll find each other and annihilate and release that energy back into the vacuum where they came. So over time, it's just a pure vacuum. But if you look in with a super microscope, you see lots of quantum fuzziness. And it's this quantum fuzziness that interacts with the boundary, the event horizon, that causes Hawking radiation.
And is it that the result of that negative charge particle falling in while the positively charged particle actually manages to escape?
Right. And when you start asking detailed questions like this, which are totally 100% reasonable questions to ask, these are the reasons why I don't like using this picture to describe Hawking radiation. And the picture I prefer to use is the one that actually tracks the mathematics in Hawking's original 1974 paper, where in that paper, he wasn't talking about pair production. He wasn't talking about a static black hole, and then there's this quantum field nearby. He's talking about a black hole when it's born. When the event horizon first forms in an emerging black hole, Some of the quantum fields that are there, just hanging out already in the vacuum, some of them get trapped near the event horizon of a forming black hole. Like they're right up against it, like a nanometer away from that event horizon. And eventually they escape
Hmm.
because they didn't fall through. They just got trapped near that boundary, but then eventually they escape. To them, it's like an instant, right? Like, oh, look, there's an event horizon. I'm gonna get away from it. But because of the strong gravity, there's time dilation there. And so, from our perspective, it can take billions of years for that quantum field to eventually escape. And because there's a quantum field trapped near the event horizon, for those billions of years, it looks like the black hole is a certain mass, but really it's not. Really, black holes are not fixed objects, they're dynamical objects. They are born, they grow, they evolve, they eventually fade away
Hmm.
because of this interaction with the quantum field that gives it almost the illusion of having a certain mass. But eventually the quantum field escapes and that pulls energy out of the system, and then the black hole shrinks correspondingly. That's not much more of a satisfying explanation, but it's the one that follows the math of Stephen Hawking's paper.
Yeah, and it's that all of that stuff is very, very difficult. Again, that's all theorized, guys. Like this is something that he was working on for a good long while, actually. And someone actually has a question here. Given the fact that a black hole can essentially be created when the density at a single point reaches a certain threshold, correct me if I'm wrong, he said, would a black hole that's being reduced in size have its mass concentration condensed as well? And
Right.
then he
That's a really
says,
good question.
yeah,
So
wouldn't that
to make a
recreate it?
black hole, yeah, to make a black hole,
Mm-hmm.
you have to squish a ball of matter below a certain radius. And we can calculate that radius. It appears in general relativity. It's called the Schwarzschild radius. For something like the Earth, if you squish it to be less than the size of a pinto bean, it will become a pinto bean sized black hole. If you take a human being and shrink it down to the size of an atomic nucleus, you'll get an atomic nucleus sized black hole. Once that happens, once you've squished the material below a Schwarzschild radius, but below that point of no return, under the picture of general relativity, it collapses to an infinitely tiny point. It is a geometric point. It has zero spatial extent.
Do we have a fancy name for this?
A singularity.
Wow.
And you
Okay.
can't spell singularity without sin, which is telling you that singularities don't really exist. They're not really allowed in nature, but this is the picture in general relativity. We know the picture in general relativity breaks down, but this is the best we got. So we have a singularity. All the mass of a black hole is concentrated in a tiny, infinitesimally small point.
Mm-hmm.
The more stuff, the more mass you cram into that point, the bigger the event horizon, the bigger the radius. But no matter the size of the radius, whether it's 1 foot across, whether it's a light year across, no matter the radius of the black hole, all the mass is concentrated in a single infinitely small point.
And how does the math work out with the singularity? Does it go
doesn't,
well?
and that's the problem.
That's the problem. So someone just said, this is all theory, right?
So yeah, I mean, black holes are a prediction of general relativity. So if you believe general relativity, and we have good reason to believe general relativity, a product of the same mathematics, the exact same mathematics that give you the precession of the orbit of Mercury, that give you gravitational waves, that give you gravitational redshifting of light and lensing and all that stuff, the exact same set of equations predicts something called a black hole. And it has those mathematics carries certain predictions about what black holes ought to look like and how they ought to behave and what kind of densities and sizes and what happens when they merge and create gravitational waves. And observationally, as far as we can tell, black holes exist.
Mm-hmm.
What's going on in the singularity? We have no idea. But black holes exist. I did a whole podcast episode called Do Black Holes Exist? Where I went back and forth between yes and no. Because yes, the astrophysical object exists. No, the singularity does not exist.
It's a yes and no, guys. And this is an interesting question. Can a black hole eat enough / collect enough mass to become a regular star again?
So what makes a star is a reality TV show and nuclear fusion. So nuclear fusion is the definition of a star. If you compress enough material together so that the temperatures and densities in the core get hot enough, they resist the inward pull of gravity. So gravity's always trying to squish a star to be smaller and smaller, but fighting against that is the energy released by nuclear fusion.
Hydrostatic equilibrium.
Hydrostatic equilibrium. I like putting random pauses in my words.
It sounds so much better when you do too.
It does, doesn't it?
Does.
Singularity.
I like it. Go on.
I like it. Yeah. So there's a balance there throughout the lifetime of a star. If you shut off nuclear fusion, say if you were just turn the switch off, like no more nuclear fusion, boom, the star would collapse in on itself and form a singularity. And you can keep piling stuff in there. You're never going to get nuclear fusion started again because the gravity is going to totally overwhelm any other forces. It's going to overwhelm the weak nuclear force. It's going to overwhelm electromagnetism. It's going to overwhelm strong nuclear. Inside of a black hole, it is gravity and gravity only does one thing, which is suck. Except for dark energy when it blows. But most of the time it sucks. And so it's just going to squish it together.
And so a lot of people ask this question, and I'm curious to hear it. So people will say, a black hole has infinite gravity. Is that correct?
A black hole in the singularity at the point of infinite density, I don't know if I would say it has infinite gravity. Maybe I would, but we know that the singularity is wrong.
Mm-hmm. But so would you say infinite density? Would you be more comfortable with saying infinite density?
In the mathematics of general relativity, it's infinite density, but we know infinite density is also wrong.
Right. Infinite is a very funny thing.
It's a big thing. Infinite.
Let's see. There's some other ones. Forgive the newbie. Oh, you're fine. But here's my
You're
question.
Cool. Welcome aboard.
Yeah, Klavitz has actually been hanging out. We've been playing puzzles. So we welcome noob questions. Seriously, I know we're talking about some high level stuff, but we go everywhere because
space is big.
Space is huge.
Have you seen it?
Just a part of it. What would happen if someone were to fall or enter a black hole?
You would die miserably. The end. Don't.
Yeah. Do you think we'll ever be able to send anything into a black hole? I'm following that question up with other questions I get.
The nearest black hole is 6,000 light years away?
Yeah.
Correct me if I'm wrong. It's far away. Unless we get supremely unlucky and have a black hole enter our solar system, that'd be good news because we get to study a black hole up close. It'd be bad news because we would all die.
Mm-hmm.
We're never going to do it.
So the next question that would follow up with that. So black holes are created as a result of a massive star collapsing.
Mm-hmm.
And so a lot of people ask, so do we have any stars around us right now that could turn into even a stellar mass black hole? Obviously it would be a supermassive black hole, but a stellar mass black hole, are we safe?
Yeah, so we're safe. I think the nearest star that's going to go supernova that could be a black hole candidate is Betelgeuse, which is what, 50 light years away?
643.
Wow, way
Yeah.
off. Okay. 643 light years away, Betelgeuse. I don't know if it's big enough to form a black hole. It might be just below the threshold. It might end its life as a neutron star, but it might become a black hole.
I think they estimate it's anywhere between 18 to like 20 some solar masses. What's the limit? What's the limit that we work with or we think? Because I know this is always changing. This number always changes.
Oh, like the biggest possible star?
Yeah, the star. Like, what's the range of stars' masses that they have to be in order to form a black hole?
Yeah, I think you need at least, what do you say, 18?
Yeah.
I think it's somewhere between 10 and 20 to make a black hole. There's some very complicated physics that happen there that determine if you turn into a neutron star or a black hole or you just blow up. And it tops out, the very largest stars must be able to form black holes because we see black holes in the very early universe, and the very early universe was only populated by very, very massive stars. So they must have turned into black holes.
Yeah, they were actually talking about something called the direct collapse idea, where just these large gas clouds would collapse, skipping the star formation process.
Yeah, just skipping all that fusion nonsense.
Yeah, just the stuff that makes us able to be here. But wait, there's some really good questions coming in now, and now everybody's asking really fun questions. Let's see. So,
nice.
How fast would you die? Quick, really fast.
If it's a stellar mass black hole, you die before you even get there.
Yeah.
If it's a supermassive black hole, you die after you fall through the event horizon.
Yeah. So stellar mass black holes, even though they're lower in their mass, no bueno. That doesn't mean they're better. Can a black hole split into 2 or 3 black holes, and do these sizes then differ definitely, or?
Can a black hole split? I don't think so. Black holes can merge for sure, but I don't think you can split a singularity, because what force is going to overwhelm all that gravity?
Right. Is there a working theory as to why there are only stellar and supermassive black holes? And so those are the intermediate black holes. Those are completely theoretical right now, but those
intermediate.
Intermediate, and those. I like it. I'm gonna start doing that too. But those range anywhere between like 100 solar masses, which, guys, is 100 times the mass of our own star, to like 1 million solar masses.
Yeah. The supermassive starts out around 1 million or so.
Yeah, and we figure that they are here because we have a supermassive black hole, and then we have these stellar mass black holes. There's got to be some kind of in between, right?
There's got to be an in-between, but if the in-between phase doesn't last long on cosmic scales, then we're likely to just never be able to see it.
Yeah.
So if it only takes, say, 1,000 years to grow a supermassive black hole, then we're not going to spot it.
Yeah. And this is another, Antonio, that's a great question. So we were talking about this earlier, and this is a big question. What was first, our galaxy or the supermassive black hole in its center?
That is a great question. The answer is we don't know. We do know that black holes and supermassive black holes and their host galaxies co-evolve. They're symbiotic. Which came first? Well, stars came first before galaxies. But did they assemble into galaxies and then a bunch of black holes filter their way down to the center and fuel a supermassive black hole? Or was there already a supermassive black hole kind of anchoring the formation of the galaxy? It's a little bit too early to tell. James Webb Space Telescope will help us if it ever freaking launches. Oh my God. I can't believe that.
I know.
It was like the last episode of Weekly Space Hangout for this season, and I spent the whole episode just like,
yeah, I know.
What?
I know. I actually streamed that here with the teleconference with the 80% confidence of it launching in 2021. This has been a big deal. Like, I was so depressed for the rest of the day.
I'm gonna be an old man.
Wait, what?
In 2020, I'm gonna be an old man in 2020.
I know. I was like, everybody's like, I'm so excited for you to stream it, Sky. And I'm like, it would be super sweet if I were streaming in 2020.
If like Twitter even exists or Twitch even exists in 2021.
I know. So in Kinger, this is another good question. Sorry, I kind of paused chat just because I want to. There's so many good questions coming in.
There's tons of great questions.
There
I love
are.
it.
I'm so proud. If space-time bends because of the mass of an object, can
True.
space-time break under a massive weight, or does it just expand into infinite? So I guess maybe this you can kind of explain the structure of a black hole. A lot of people ask me like, is it a hole or is it actually a sphere or what is it? You know, the people because the way we see it portrayed, you know.
Yeah. So a black hole is a 3-dimensional object. So the event horizon, it's a ball.
Mm-hmm.
The event horizon is a ball. It's a radius, so you can go up to it. You can circle around it just like you would circle around a star or a planet. The singularity itself is a geometric point. It has 0 spatial extent. So that really is almost like a puncture in space-time itself. And then in between the puncture in the event horizon is really, 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 really bent space. So imagining structures in 3 dimensions is actually kind of tricky. Imagine a funnel. You can think of a funnel in your head. That is a 2-dimensional, that is a bending of a 2-dimensional object, right? You take a piece of paper and you pull down the middle, you can make a funnel. Now do that in 3 dimensions.
You take a piece of paper and you fold it. I have a piece of paper.
You have a piece of paper.
I do.
So maybe a piece of paper isn't the best idea.
Okay.
Do you have like a rubber sheet?
I have spandex. Like I do the thing. Wow. Okay. Hold on. Before you start judging me. Okay. Just 1 second.
I'm just going to lean back and let this play out.
I have a hula hoop with spandex covering it so that people can see.
Okay.
Yeah, so you can put a massive object in the middle and roll marbles across it so you can show how things move in space. But it's not accessible, so I mean I can get it.
Fine.
But yeah.
Your spandex hula hoop, whatever you do on the weekends, is inaccessible on the moment it's at the laundry.
Right.
So that is you take a 2-dimensional thing and you sink a weight into it and it gives you some sense of a curvature. If you do that, if you take a 3-dimensional thing and bend that gives you what general relativity is actually doing. And you also have to bend the dimension of time. So you're bending 3 spatial dimensions in 1 dimension at a time. This is why mathematics is so nice, because you don't have to actually visualize things in your head. You can just crank out the math.
Yeah. So wait, let's see. There's so many good questions. I'm scrolling up right now. Sorry, I lost my place because I wanted to go down to see everybody laughing at me about the spandex.
And Vidimus OKC, vector math. This is actually tensor mathematics in general relativity.
Oh, so Debauchery says, why would a smaller black hole kill you before you would get there, whereas a supermassive because supermassive has a larger event horizon, right? Mm-hmm. Yeah.
So it's because all the stuff is in the singularity. Mm-hmm. All the stuff is in a tiny geometric point. But the radius of the black hole depends on its mass. So for like a stellar mass black hole, you've got the singularity right here and the event horizon like right next to it. Mm-hmm. So by the time you get up to the event horizon, you're really close to that singularity. There's extreme gravitational differences and you get torn apart.
Yeah.
With a supermassive black hole, all the stuff is here in the center, but the event horizon is way out here, where the gravity differences are actually kind of minor because the singularity is way down here. I'll put my hand in the corner.
Yeah, I was going to start moving it, but I'm like, no, I'm not touching it.
Don't touch it.
Okay.
There we go.
Okay.
So that when you're near the event horizon way up here, you're really far away from the singularity.
Yeah. So you don't have as much wiggle room with a stellar mass black hole.
Yeah.
And there's Starman says, do you think micro fluctuations in Earth's gravity contribute to a form of time dilation that makes our days really long or good times really short? I don't know if that's a serious question. What's on the other side?
Max, can someone just say Spaghettification.
Vacation. What's on the other side of a black hole? We do not know.
We can. Oh well, there's just space.
Yeah.
And then there's a singularity, and that's it.
But we don't even know if that's really there.
We know the singularity isn't there. What it's replaced with, we don't know.
Okay.
But between the singularity and the event horizon, it's just space.
Okay.
Really, really bent space.
Would there be tiny black holes left over from the Big Bang? How small could they be?
That is a very, very interesting question. So, as far as we know, black holes are only formed through the deaths of massive stars. There is a possibility that exotic processes in the infant universe produced a lot of black holes. They might be, I don't know, a few kilograms, which means they would evaporate by Hawking radiation in, I don't know, 10 billion years or so. Like, hey, that's the age of the universe. So we might see little bleeps and bloops of small black holes evaporating. We don't see that. We don't see any signatures of small black holes evaporating. So we don't think these black holes were produced in the early universe.
And then someone said, wait. So therefore, Give Bacon says this.
Don't tell me.
So therefore, if a black hole is introduced to a larger black hole, could the bigger black hole, instead of absorbing the smaller black hole, can it split it first? Maybe before it absorbs it, like splitting the smaller black hole?
I don't think so, because once you make a singularity, I don't think you can make two singularities.
Ooh.
And that's what it really means. That's what it really means. The black hole is the singularity. The black hole is a feature in space-time. If you think of it as a puncture in space-time, you can take two punctures and move them together to make a single puncture, but you can't take a single puncture and stitch the fabric in between to separate them out.
Okay, sorry, there's people doing yard work, so it gets really loud here for a second, but like that. So I'm going to be lowering my mic in and out, so sorry, guys. Do we have any images of our Milky Way black hole feeding? We don't.
Not yet. We do have evidence that it fed in the past. It left some mess. These are called the Fermi bubbles. These are giant bubbles, tens of thousands of light years across, of very, very thin but very, very hot gas that have been ejected from the core of our galaxy. And we think it was a feeding event somewhere around 50 to 100 million years ago, if I remember right.
Yeah, so right now it's on a diet, though.
Yeah, it's trying to cut back a little.
Yeah, it got a little bit overzealous.
It went keto, and it's trying to shape. It's summer.
Yeah, it's
galactic summer.
Summer somewhere, everywhere.
Summer black hole bodies are made in the winter.
Can someone just say, we already did. I'm sorry, Mig. Like totally. That's how slow I'm scrolling here because there's so many good questions. You guys are amazing. So therefore time, wait. Give Bacon has another one. So can time be measured in a black hole or not since it breaks space-time? Does it break space-time? Does it rip it? What does a black hole do to space-time?
So it bends it really, really bad. In the singularity, it's technically broken, but singularities don't exist, so we don't need to worry about that. If you have a watch strapped to your wrist and you fall into a black hole, that watch will keep ticking. And in fact, one of the crazy things about a black hole is inside of a black hole, all paths lead to the singularity. No matter what you do, no matter where you turn, no matter where you fire your rockets, you turn around, whatever you try to do, all of your future fates end in the singularity in a finite amount of time. So if you were to fall into a supermassive black hole, as soon as you cross that event horizon, you have about 7 seconds until you hit the singularity, and there's absolutely nothing you can do about it. And that is 7 seconds according to a watch on your wrist. So you just start counting, in 7 seconds, you're obliterated.
Wow. 7 seconds. So let's see. there's another question. Have we ever seen any kind of black hole evaporate entirely? We have not. That is all
We have
theory.
not. Negative on that.
Yeah, and that would take a long time. And even in the theory, they say that black holes would likely be the last thing to go. Right?
The last macroscopic objects.
Yeah. So Fenring says, which effect contributes more to the GPS satellite clock correction? Smaller effect of Earth's gravity or high orbital speed?
If I remember correctly, you're absolutely right. There's two effects for the GPS. There's the special relativity effect of the satellite going really, really fast, and the general relativity effect of weaker gravity up there. They counteract each other. I think the going fast is twice as significant as the general relativity height difference, if I remember right.
Yeah. Let's see.
But you need both. You need both in order to make them accurate.
Right. So Einstein was right.
Again.
I mean, I really wish he would just stop being so right.
Really, the 20th century is the story of us trying to prove Einstein wrong and failing.
Pretty much.
With the exception of quantum mechanics.
Yeah, QM.
Einstein was dead wrong about quantum mechanics.
Well, he again, there's infinity.
There's infinity. Don't get me started. Oh, quantum field theory is a hot mess. I love it, but it is a hot mess of a theory. But Einstein was never a fan of quantum mechanics. And my entanglement episode just came out today.
Ooh, congratulations.
And I talk about this, how Einstein did not like entanglement, but there's some heavyweights in quantum mechanics that proved him wrong.
Yeah. I think actually Hawking, and I could be wrong on this, I don't think he was a fan of QM either. I think he liked dealing more with the large scale things, and then he kind of was forced to get into the QM with the Hawking radiation stuff.
Right. So Hawking was really, really interested in the nature of gravity, and especially the nature of strong gravity. It turns out if you want to examine the nature of strong gravity, you have to use quantum mechanics and quantum field theory language to do it.
Have there been any attempts to reproduce the formation of a black hole on an entirely small scale? He's probably referring.
I hope not.
Yeah, I think there's some talk, like some people come in here and ask about, can the LHC, so if you guys don't know what I'm talking about, sorry, I acronymed it, TBH, OMG,
Lick.
IDK, but the LHC is the Large Hadron Collider. And I've heard people say, well, can they make a tiny black hole? A microscopic one?
You don't want to go there.
But that wouldn't do anything. It would pop in and out of existence like that. It would go. It wouldn't be a problem.
Yeah, it'd evaporate from Hawking radiation.
Yeah.
And Unicorn Lover, why do I feel like I'm in the Big Bang Theory? That's because you're not laughing at any of the jokes.
I'm just laughing that you just said Unicorn Lover.
Unicorn Lover 6996. Because there's 6,995 others. And this one was late to the party.
Can you explain why black holes are needed for us to detect gravitational waves?
Oh, they're not. We like black holes as a source of gravitational waves because they're really massive and really dense, and they make really, really big waves. But other objects colliding also make gravitational waves, like the neutron star merger announcement from last year. That didn't involve any black holes. Supernova make gravitational waves. That there's going to be a big search to look for supernova with the gravitational wave detectors. There's remnant gravitational waves from the Big Bang itself. There's all sorts of gravitational waves sloshing through there. It just so happens that black holes make the biggest.
And this guy's been asking this question. I've been kind of dodging it, but I'm going to just ask it because he's going to keep asking.
We'll dive head on. We'll do it.
I don't even know how to pronounce his name. I think it's Roggs, but correct me if I'm wrong, Roggs. Holographic universe theory. And Event Horizon. So he did actually put those two together. So he married the two that, and so it's not an or. It's universe theory and event horizon.
So here's the deal.
Mhm.
There's something funny about black hole event horizons. So not all the funny business is in the singularity. There's also something funny about the event horizon. That if you put one bit of information inside of a black hole, and we can define that quantum mechanically, but I'll leave that for another day. You put one bit of information inside of a black hole, it grows, which is not surprising at all because you put something in a black hole. But the way it grows is very surprising. If you put exactly one bit of information into a black hole, its area grows by exactly 1 Planck unit squared.
Math.
So, the Planck length,
Well, yeah,
fundamental.
But some people might not know what you're talking about. You're starting to speak another language.
I am speaking another language, but you asked about holographic theory. And so here we are.
I didn't. Rox, look what you did. Okay, so go on.
You brought it out. So the Planck length is this interesting quantum mechanical length unit. You can kind of sort of think of it as the fundamental length unit of the universe, but not really, but okay. What's interesting about this statement is that if you put one bit of information in, the surface area of the black hole grows by a fixed amount, not necessarily its volume. So there's a connection between the amount of information in a black hole and its surface area. There's not a connection between the information and its volume. There's a connection between the information and its surface area, which means maybe you can totally describe a black hole by its 2-dimensional surface instead of its 3-dimensional volume, which is holographic theory, where you use 2 dimensions or lower dimensions to describe objects in higher dimensions.
I feel like that's kind of half the problem, right? That's why people have such a hard time imagining this, because a lot of the things we see are represented in 2D.
Yes.
And so this is...
But a black hole is really a 3-dimensional object.
Yes.
Just like a planet. Imagine if you could describe the entire, capture all the information about a person by just looking at their skin.
No.
Imagine. I want you to imagine. It's not accepting or rejecting that. You just imagine it.
Okay.
Imagine if that were true. You knew all the state of their organs. You knew what they had for lunch. You knew, their heart rate just by looking at their skin. That is what a holographic description would give you.
In.
And it's like a black hole. With black holes, it looks like just by looking at the surface, by looking at the event horizon, we can see what it had for lunch.
No, I think that does already kind of exist, and that's called Facebook.
Yes, there is that. So that's a voluntary holographic projection.
There you guys go. Solved. Okay, we write this one off.
Holographic projection.
Face.
Volunteer. Book. And then the whole holographic thing goes, well, that's interesting. Maybe we can apply it to the whole universe and solve quantum gravity.
Okay.
There's a big jump there.
Actually, that's good though. That I agree with. I agree with your description. However, I don't want that power ever. Someone says probably a new question. It's okay. It's totally fine. But I
only want repeat questions. I just want to say the same things over and over every Tuesday.
Here. Please, guys.
I want to put this on Rails. I want to record it, and then I can just go do other stuff.
Yeah. No, I do this live and for a long time, so I start messing up information. This is probably a new question, but on TV they show the diagrams of a black hole. Every star that moves over is still there once the black hole passes over it. Is that what really happens? If so, why isn't it destroying every star? This is a good question, Animus.
It's a great question. That's a great question.
Because people are like, well, that's weird because we found our supermassive black hole by looking inside through the gas clouds that are really annoying, and we looked at the center. Super annoying. Yeah, they're pretty, but not for looking when you want to look at things.
Same for the atmosphere.
Yeah,
I mean,
it's annoying.
Do you know how hard the atmosphere makes astronomy?
Yeah,
this is getting out of hand.
It's really
Someone should
bothersome.
clean that up.
Mm-hmm. And so we have to look in different wavelengths of light to be able to look at those stars. And those stars are moving around that supermassive black hole, and they're whipping around it. You know, their velocity is changing
really fast.
As they're going closer to it, they get that gravitational assist. But why? You know, this is a great question because why are they not falling in?
So. Great, excellent question. In response, I'll ask a question of my own.
Ooh.
Classic teacher move.
Yeah.
Why doesn't the Earth fall into the sun, young grasshopper?
And then I'm gonna ask you that question. Why doesn't it?
And I will answer my own question that I posed to you.
So why doesn't?
We're in orbit around the sun. So we're in balance. The sun is gravitationally attracting us, but we had energy at the start of the formation of the solar system to give us a kick, kinetic energy to give us oomph. So we stay in a stable orbit. If you were to take the sun and just replace it with a black hole,
we'd be fine if it's one solar
other
mass.
than like all of us dying.
Right. Well, getting cold. Yeah.
And getting cold. I mean, yeah, we could do hydroponics.
Mm-hmm.
We could make it happen. Mm-hmm. The only thing we would get to eat is marijuana because that's what we have the most proficiency at growing indoors. So we'd have to get used to that. Mm-hmm. But other than that, our orbit would stay exactly the same.
Yeah. I'm sorry, but that sounds like a lot of fun. Why don't we just go ahead and just, get to it now? Our sun's never going to create a black hole, though.
It's not. It will kill us in far more interesting ways.
Yeah. I love this guy. He just won my heart. Yes, he's amazing. And he's on every Tuesday. He has his own stuff. So if you guys want to find how to find him, that guest command. Stuff. He even has Paul. He has his own command too. See, look. Wow, magic.
Boom.
So we're able.
I love it, cheese connoisseur.
Yes.
I don't want to give the impression that I'm like some fancy cheese sommelier, fromagerier, whatever it is.
You're not even.
I just enjoy eating all the cheese. I don't even know what it is half the time that I'm shoving in my mouth. That came out wrong.
And only on this stream is that really totally fine. This is such great stuff.
And Emmentaler is just Swiss with a fancy name. You can't fool me, Emmentaler. You're just Swiss cheese.
So Brian says, so if I understand correctly, one can indirectly determine the mass, charge, acceleration, surface area, volume, angular momentum, and temperature of a black hole. What information is lost then? The number of, it says moles of certain particles?
Yeah, so this is the big question. This is the hot debate amongst all 4 black hole theorists in the world. Mm-hmm. Is what happens to all the information that falls into a black hole, because black holes themselves are ridiculously simple. And is all that information just get gobbled up? But then if it gets gobbled up and then eventually evaporates, where'd it go? Because we don't think we can destroy information. Does it just get glued to the surface? Well, if it just gets glued to the surface, are we really understanding black holes in the way we think we are, et cetera, et cetera, et cetera?
If dark matter has not been directly observed, why do scientists feel the need to propose its existence?
Ooh, switching gears here.
Yeah,
because
we can
use it. This is great. Dark matter has not been directly observed. That is correct. It has been indirectly observed. So when we look at the motions of stars inside of galaxies, and we look at the motions inside of galaxies, inside of clusters, when we look at the temperature of hot gas in between galaxies, when we look at the large scale structure of the universe itself, when we look at the way the path that light will bend around massive objects, there is stuff in the universe that is not all hot and glowy.
Mm-hmm.
There's just, if you just add up all the stars, all the glass clouds, all the black holes, you add it all up, you can't explain all these dynamical effects that we see in the universe.
Yeah, that's only about 5%, all this stuff in the universe,
Yep.
that ordinary matter.
You're coming up short every single measure. Totally independent methods, totally different corners of the universe, totally different scales, totally different physics. Every single time we come up short in our mass estimates. And so we're pretty dang sure there's another form of mass out there.
And so dark matter, so people are asking, so since we don't fall in on a smaller scale in our solar system, we don't fall into the sun, we go around, would you call that the conservation of angular momentum that keeps us kind of going?
Angular momentum
asked
is
that earlier.
Yeah, angular momentum is conserved. Yeah.
And then also on a larger scale, so we'll say our supermassive black hole, is that happening with our solar system going around on the Milky Way, which is, I think, about every 250 million years.
Yeah,
our solar
300 million years, a single orbit.
250.
Which I saw an announcement, like someone somewhere is trying to define a tick, which is 1/100 millionth of an orbit around the Milky Way. So it's like every 3 years or so.
Uh-huh.
Yeah, no, that's it.
Huh.
And they're like happy tick day or something.
Cool.
Yeah.
Great. So is it the same kind of thing? Is the supermassive black hole? Someone asked this in earlier, and I wanted to log it in my brain. So is that kind of the same thing happening here, or is the supermassive black hole responsible for us going around as a solar system on the Milky Way?
So our supermassive black hole is big. It's a few million times more massive than the sun. If you were to pluck it out of our own Milky Way galaxy, absolutely nothing would change in terms of orbits or dynamics.
Mm-hmm.
The black hole is big. Our galaxy is tremendous. Our galaxy is at least 10,000 times more massive than the supermassive black hole in our center.
Mm-hmm. So is dark matter also something that is kind of keeping things going too, maybe?
Absolutely. So it's if you look at, so our speed, this is like a primary evidence, one of the first pieces of evidence we had for dark matter. If you look at our speed in the Milky Way, we're going somewhere around 200 kilometers per second, if I remember right, in orbit. And if you look at all the stuff inside of our orbit, all the stars, all the clouds of gas, everything, and then you just apply Kepler's laws, Newton's laws, basic physics, there's not enough stuff to give us that kind of speed in orbit.
Yeah.
There has to be more stuff inside our orbit than we can see to give us our own speed in our orbit.
Thank you for adding that. It's perfect. Thanks. Yeah, I know. Let's see. So, and some of these questions, I can answer too, guys. So if I'm skipping over, I'm just ask again. Yeah, we deleted the sun yesterday, and you saw what happened. Planets just go on the course that they were on.
We didn't see because it was dark.
Well, yeah. Well, I did a simulation of it. So.
Oh, okay.
Let's see. Is there a black hole opposite, aka white hole?
White hole. So in the mathematics of general relativity, you can generate white holes, which are regions of space-time that reject all matter. So they're still gravitating objects. So they're still a massive object, but nothing can fall into the event horizon. As far as we can tell, and I'm pretty sure on this, white holes don't exist in our universe, unlike their cousins, the black holes, because white holes are incredibly unstable. Where if you were to set up a white hole, you can make it. Then you were to take just one tiny little electron or photon, just one little bit of matter, and bring it into the white hole. As it got closer and closer to the reverse event horizon, the energy in the system would go higher and higher and higher, and eventually it would go to infinity, and the white hole itself would destabilize and tear itself apart.
Yeah. Complete inverse, and we have never found one. We don't believe that. Yeah.
And we don't think they can be stabilized.
They can be stable. Yeah. Same thing with a wormhole. Like, everybody's like wormholes, and
wormholes.
Yeah. Stability is also an issue there on the theoretical side of it, right?
Yes.
Yeah.
For sure.
So let's see. Someone had a good question because, playing into the dark matter thing we're using it still while talking about black holes, which is kind of funny. Well, we're talking about things on the galactic scale.
We're talking about stuff that doesn't glow.
Right. And so if you look back while falling into a black hole, would you see? You'd see the universe go by. But then you have the conundrum of if time goes by, then where's the black hole?
So
your frame of reference,
the clock on your wrist will tick by, you will fall into the black hole, and you will die.
Right.
Someone watching you from far away.
Say me. I'm watching you. You're going
I don't know. Why can't it be the other way around?
I don't like this. One time I'll fall in. Okay. So you can be you can be eating your Cheetos on the spaceship this time, but just this time,
Thank
once.
you. I appreciate it.
Okay.
Now, as Sky falls into the black hole, I see her get slower and slower and slower. I see the light coming from her. She's shining a flashlight saying SOS.
And he's not helping.
And I'm not helping because I got Cheeto dust and I don't, I gotta go wash it off. And anyway, I'll get to it. That light gets redder and redder. She gets slower and slower. And to me, from my perspective, she never crosses the event horizon. She just becomes infinitely redshifted and infinitely slow and just kind of smeared all over the event horizon like cream cheese on a bagel.
Yeah, I just freeze. Do you? At some point. And then he just continues eating his Cheetos. Now, me looking back out at you, though.
You looking back out at me, you see a sped up universe.
I see time go by.
You see time go by. You see me eat the entire bag of Cheetos. Don't judge.
So fast, too.
You see me like that. You see me wash my hands. You see me shrug my shoulders. I guess you're not coming back. Power up the spaceship and go in the span of like 3 seconds.
Yeah. And then, but this is the question. So let's say I didn't die. Let's say I didn't die and I saw the universe.
You fell into a supermassive black hole.
Well, I'm not at the point. I'm getting closer, but I'm seeing time go by looking back at you. Does my black hole end up disappearing at some point?
No, because you don't. If you're freely falling into a black hole.
Like Tom Petty. Go on.
That's exactly what the song was about. You see the universe sped up, but you don't see the universe sped up to infinity.
Okay.
You see the universe sped up a lot. There is a question of, in this sped up universe, there's going to be a lot of high energy radiation pouring into your face. And so maybe the gravity won't kill you, but the radiation will.
One hell of a tan.
Like your bones get tan.
Yeah, like my DNA is no longer
bone
even.
Tan.
Yeah, it's not even.
That's
DNA.
what I want. I want bone tan.
Yeah, that's what I'm
I
looking for.
want a marrow tan.
So
there is that, but it's not. You don't speed up the universe that much.
Okay, good to know. You want a tan on your tan, right?
Tan.
So, guys, he only has about a minute left. Do you want to take one more question?
I'll go a little bit longer.
Oh,
I'll
you
go
will?
a little longer.
Yay!
Yeah, I'm chilling in my house.
Yep.
Took
With
the
his
day off.
chalkboard, you know. If you had to guess what's your favorite candidate for dark matter? I'm not sure.
It's likely a wimp, but it might be more complicated.
Oh, the weak interacting. Okay. I get what that. Yeah. Let's see. Well, there's someone who was asked more questions about white holes. And someone else was like, "That's a good question. If a white hole rejects mass but it still has gravity, can it be a negative value? Can gravity be a negative value?" Wow.
Gravity can be a negative value, not in white holes, but gravity can be repulsive in some very, very curious situations. We're experiencing such a case right now with the accelerated expansion of the universe, which is repulsive gravity.
Right. And again, white holes do not what?
White holes are not going to have repulsive gravity.
Oh, right.
But white holes, you can't get within. They still pull you in, but you can't get within the event horizon.
And just to make sure that we're just saying this again in case someone just walked in and they're like, "So white holes do exist?"
No.
Okay. Just making sure.
Just want to be sure. We'll say it every 45 seconds.
Every time
like
we
a
mention
TV
it.
show. Yeah, like you come back from commercial and then they recap what you just watched, even though you just sped through the commercials on fast forward.
Right. And then that's the one where they assume that everybody's just dumb and they have to repeat the whole storyline like at least 5 or 6 times.
Which probably right.
Yeah, true.
And you gotta kill some time. I mean, you gotta fill up 43 minutes of airtime, and man, why not just create 30 minutes of content and then repeat yourself
over and over again? At least 20 minutes of that content has to be just repetitive things that you've seen prior. So I've been told I am wrong. When I see, I've been told I am wrong. I see what we see as space as objects traveling through a gravitational field, like you are in a pool. Objects.
Oh.
Do you want to just start from that, and I can continue on?
I see what we see as space as objects traveling through a gravitational field. You're in a pool. I'm reading it quietly to myself.
Mm-hmm. Time is just a measurement of change.
I'm not finding a hook to argue against it. So, in the perspective of general relativity, gravity is the distortion of space-time itself. And that's bending of both space and time.
Okay. Let's see. If you fall into a black hole, you can always fire up your warp drive to fly out. Thanks, DPI. Thanks.
Yeah. So if you have your magical science fiction thing, you can do different. You can break the laws of physics. Who knew?
And here's another question. So I had somebody ask me, is time just an illusion? What is time?
That is a tough one.
Oh God.
That is a tough one. And I'm actually like sketching out either a 1 or 2 part series for Ask a Spaceman about the nature of time.
I think that might be a 2-part.
It's probably going to be a 2-part because I did an episode about why time travel isn't a thing. And that's pretty straightforward. But then you immediately get into this question of just what is time? And it appears in our physical theories the same way dimensions of space do. Time has a few odd properties that it doesn't share with space. Why do we experience this flow of time? Is it fundamental? Is it subjective? Is it, what's the connection here? Why is past time travel not allowed? I get the sense in the physics community that this is something we ought to be able to figure out, and something that maybe a theory of everything or a theory of quantum gravity might give us some hints about the nature of time. And we have a few very interesting threads, but there's nothing really conclusive to say about the nature of time.
Yeah.
From a physics perspective.
Yes. Except your face. Someone just asked.
Oh.
No.
I accept my face. No, you spelled it right the first time, Joe.
Yeah. So someone said, can a black hole speed up the speed of light, travel faster than its limit? No, the speed of light always travels at the speed of light. Nothing goes faster.
Speed of light, speed of light.
Yeah. And what do you feel about tachyons before tachyons are mentioned?
The same way I feel about unicorns and fairies.
Okay. And white holes and warp drive?
And white holes and warp drives.
Wormholes?
And wormholes.
Okay. Just making sure we're just tachyons.
Speaking of time, I'm actually working with a modern dance company in Manhattan called Siren Modern Dance, and we are doing a production about the nature of time. So we're going to start choreographing that actually in about a month. And in 2 weeks, and if you're in Manhattan in 2 weeks, we're going to have a little kickoff event. I'll send the link.
Wait, yeah, please do. But wait, you're going to dance?
I'm not going to dance. No one wants to see that.
Okay.
But so I've done this before. So I created Song of the Stars, which is a dance performance, a contemporary dance performance theme from the life stories of the stars. And this is going to be a modern dance performance about time, about the physics of time and how we perceive time and what time means to us. It's going to be really fun. We're aiming for the first weekend in December for the first public performance, but there's a little kickoff event in a couple weeks in Manhattan.
Awesome. Joe, can we add that actually to the command just so we could put it in there? Please, Joe. But someone give Bacon, and also thank you, Give Bacon, for referring Smiley's question. I appreciate that. Sometimes I miss things. Sometimes it's intentional, but that wasn't intentional. So sometimes that does happen. So thank you, Give Bacon. So if I fell into a black hole, see, now he just wants to talk about me falling into this black hole. So
we want return to this theme of you dying a horrible death.
Thanks, guys. I really love you too. But if she fell into a black hole, would she not be that bit of information that we drop into the black hole, increasing the 2D size? Oh, so he's giving me significance. Okay, I take that back.
You mean something.
I mean something.
Yes, the black hole would get bigger.
Does that mean that I'm fat? I'm kidding. I had to. Yeah. And by the way, you're subscribed to my channel.
No, you're
now?
fat when the black hole falls into you.
Yes. That's how one gets mass, guys. Yeah. Alan just gifted you a sub, Dr. Paul, to my channel. You're back for 4 months and you didn't even know it.
Nice. I think I have like 10 years worth of subs on your channel, I think.
If you have Amazon Prime, do you have Amazon Prime?
I have Amazon Prime.
Then you can do a free sub.
I think I alternate between you and Pamela.
Oh, okay. Okay. Well, Alan coming in strong, keeping you at that 4 month. Thank you, Alan.
Appreciate it.
Let's do, how much time do you have? Do you want to say like another 10?
Few minutes.
Few. Okay, 5? Handful? Okay. It's interesting. Let's see. Well, wait. What light do we always refer to? Like, is there a specific wavelength when referring to the speed of light? So this is all light.
Good question.
Yeah.
Yeah.
You can look at my arm real quick. Go ahead and talk about this.
Yeah. So you have a diagram built in, very handy. It's all wavelengths. All wavelengths of light travel at the exact same speed.
So this is all light.
All of it.
All of it. And so it all travels at C. 186,000 miles per second or 300,000 kilometers per second.
Or 1.
Or 1. 42.
1 speed of light unit. So most advanced physics, you'd get tired of carrying that C around and all the equations. So you just set the speed of light equal to 1. And this is known as geometrized units. And this is my favorite thing, because if you set the speed of light equal to 1, then you recast everything to be in terms of distance. So an object could be 3 meters away in both space and then 4 meters away in time. And then even things like mass get reconverted into distance. And in the system of units, which is far superior than metric or imperial or whatever, in the system of units where the speed of light equals 1, the mass of the sun, are you ready for this?
I'm ready.
The mass of the sun is about a mile.
Brain did not want to do that at all.
No.
No.
Isn't that great?
That's amazing. Wow. Wow,
If
bruh.
you set the speed of light equal to 1, the mass of the sun is a little less than a mile.
Wow. Jeez. Let's see. There's a good question going along with this. Okay, so we'll do 2 more questions and we'll call it. If light can be slowed down, I can answer that. Yeah, it can if it's traveling through a certain medium. Like water. Water would slow down a photon.
Totally slow.
Is it possible that light can completely stop?
I don't think so.
Okay.
You can set light in orbit. So neutron stars and black holes can have light orbit them.
Yes. Sorry, I was being responded to on that. So let's see. So one more question.
I see. I'm confusing everybody with the mass of the sun being a little less than a mile.
Yeah, brain doesn't want to do that. It's okay, guys. We'll have him explain that.
Another day. Another kilometer.
Yeah. And
yeah.
Let's see. I'm trying to find an easy one to answer. Nope. God, you guys are asking really technical questions now.
Sweet.
I think we're good. I think we're good.
Let's just call it quits.
Yeah,
guys.
we're just gonna throw in the
Over
towel.
it.
I'm still gonna stay here.
We're done.
Yeah, he's gonna go get back to what are you doing? The rest of your
Remodeling
day?
my patio.
Wow, you are so
Been
domestic.
been doing it for like a week.
Well, last time it was gardening.
It was gardening and then prepping for the big remodel, and now it's almost done actually.
Okay.
Tons of stuff. I built a pergola.
Whoa.
Yeah.
Wow. Okay.
It was a kit. I mean, it's not like I made it out of wood, but it was a kit.
It was a kit, guys. Well,
I built
thank you.
a pergola. I did build a boardwalk, which I'm very proud of.
A boardwalk?
A boardwalk out to our pool.
You have a pool?
We got a pool. Yeah.
Okay. Well, I got mountains. But yes, guys.
There you go.
Guys.
Well, I got mountains.
It's not even. I'm just trying to one up you, and it didn't. I'm not even convinced of my one up.
Did you build those mountains in your backyard?
I made them.
You made those mountains.
I made them. So yeah, guys, Dr. Paul, he's on every Tuesday, except again, if he's traveling or I'm traveling or we're traveling or whatever. But even when he is lately, we've been around.
Remarkably consistent.
Yeah, we have. And so you guys can find him again, the guest command or, exclamation point Paul. And thank you so much for
Thanks
hanging
again
out.
for having me on. Tons of great questions. This was lots of fun.
It was. All right. Well, I will talk to you soon.
Take it easy. Have a good 4th of July.
You too.
Hey, everyone.
All right. Bye.
Bye.
Okay. Let's see.